So hopefully everything went well in lab last week. Were there any issues? If you haven't sent me your group member names, please do so as soon as you can. I think I'm still missing groups for about a third of the class. I assume everyone's got a group, but the ones that haven't told me yet haven't told me, just forgot. So today I don't have any new material, so my plan was to go through a little, like a live demo, because I understand that Philip and Charles have been doing that in the labs, which is good, except if they're doing that, you're not necessarily able to work, in the lab and take advantage of the TAs being there to ask questions. So I thought I would do, I try to take a little bit of that load off of them and do a live demo in here. And in case anyone is completely lost, or maybe you missed lab last week, hopefully this will help you out. All right. So any questions, by the way, before we get started? Okay. So if you go to Dropbox, we have the Lab 1 skeleton that you can download, which I'll just go through that real quick here. We need to do something about how this page is organized, but this is the lab UART. I don't know if you can see that in the back. Probably should change the resolution. The last link on the page here is the labuart.tgz, and you can just download that. And then Charles gave out a copy of the boilerplate code for the UART, UART being the console code that I gave you in the slides. And he also gave you, I think, in the handouts. But if you copy and paste from either the PowerPoint slides or the handouts, the code gets all mangled. So he has a copy here in the announcements under code listings as promised. And he's got it right there. So I will go over to, over here. So I downloaded that. Go to downloads and untar this. And there's a directory called labuart. And this has got everything you need to build your project. If you look at main.c, this is, well, that's kind of hard to see. Right. Profile preferences here. Yeah, there we go. Thank you. Colors. Let's see. Let's do black on white. That's probably the best. Is that better? Yeah, a little better. Okay. So Charles, thank you. Charles has the some comments here that are placeholders to try to help you start to get to work. But we don't actually need this right now. In fact, I'm just going to go to the code that he provided in the announcement. So I'm just going to take all this and code listings. I'm going to take all this and paste it in. Now this is kind of this is something that I really don't like, but currently the only way to debug your code is through what I call Printf Debugging, right? Where you have the terminal boilerplate code, and then if you run into a problem, you can print messages out to try to diagnose the problem. That's not ideal. Ideally, we'd be able to use a debugger, but we haven't gotten the debugger functionality working yet. It's something we ought to be able to do, but it's not working. So generally speaking, you're always going to want to have this boilerplate code in until we have debugging capability. Otherwise, if things don't work, you really have no way to diagnose the problem. So can just paste all that in and then get rid of the original main. Okay. All right. So the other thing is we've got this. I don't know if you noticed. There's this little line of hyphens. You need to get rid of that. And then could probably move these includes up to the top where they should be, and we already have them. So that's interrupt io.h. I've already got io.h Standard lib, I already have that. String and I don't have delay. I do have delay. Okay, so there we go. All right, so now I've got this. I should be able to UART lab, right? Lab UART. I should be able to do a make burn for this. Now I got to get my board plugged in first. So plug that in one side. Put this in the other. Okay, and one other thing I got to do before I do that. If you ever have issues with your board, you could do a quick sanity check. If you type LSUSB, you should see the Atmel ICE debugger listed there, right? And in my case, I need to change the permissions on that file, because this doesn't happen automatically on my machine. Let's see, that would be bus 1, device 3. All right, so now, before I do that, also, I want to open up another, I want to run picocom -B 57,600 dev tty USB 0. Okay, all right, so those are print messages from the previous code that I was running on it. All right, so I should be able to do a make burn, and it looks good. All right, so it burned it and it programmed it. Now, what is supposed to be happening here? If we go back up to the code, so if we go down to the main function, the only thing it's doing right now is setting the data direction register on port C to 8 ones. So actually the port C is actually only 7 bits, but there's no harm in setting 8 ones in there. So this is setting all the outputs of port C to an output. And then there's a while loop that loops forever because it's a while 1. And then we set the port C, which is the output, to 8 ones, so all 7 bits of port C are set to 1. Then there's a delay of 100 milliseconds, 1/10 of a second, and then it sets it to 0 and repeats. And so if you look at the board, I just took an LED and I literally just jammed it. Well, actually, first thing I had to do was I had to figure out where port C was, because I don't know where that's at. So if you bring up the diagram of the board, which is right here, you can look on there to identify where the port C is, and that's right over here, PC0 to PC5. So that's the header that's on the lower left-hand corner. So I took an LED, and in this case, since we're driving all 6 or 7 pins of port C, I just took an LED and I plugged one end into one of these port C pins and the other end into ground, which is right above port C, conveniently located. So that way you can see the thing, flashing. And so it's turning on for 1/10 of a second, then turning off for 1/10 of a second. So the period here is 1/5 of a second, right? Any questions about that? Okay, so what else can I do with this simple setup? Well, how about the timers? I'm not sure how far you guys have gotten in lab with the timers. So if you remember from the lecture, if I can find the spot, there are 3 timers on the board. And the timers are pretty versatile. You can use them to count Here they are. Yeah, you can use them to count external events that come in from a pin outside the board or outside the chip. You can use them to count cycles and to run off the internal oscillator. And so when you're doing that, you can use it for things like timing, like very fine-grained timing. You can time things with the granularity of the clock, which is 1/16 millionth of a second. Or you could use it to delay or that kind of stuff. So there's 3 of them. There's a 16-bit timer, a counter, which is counter 1, and there are 2 8-bit counters. That's counter 0 and counter 2. Now, one of the problems with these counters is that they're really small, right? So you imagine that if you run them off the internal oscillator, they're going to overflow really fast, right? So one of the things you can do to slow things down a bit is you can set a prescale, which will count up once every cycle, but you can have it count up every 8 cycles, every 64 cycles, and every 1024 cycles. But even then, if you're timing things that a human being would be doing, even every 1024 cycles is pretty fast. In fact, so that would overflow. Let's see. So if you have the 16-bit counter, 65,536, right, is the max. That's when it'll roll over. And then if you multiply that by 1024 and then you divide it by 16 million, it'll roll over in 4.1 seconds, even if you apply the 1024 prescaler. Does that make sense? Okay, so that's pretty fast. But you can actually use a trick to make those counters appear bigger. And the way you can do that is you can use you can trigger an interrupt whenever the timer rolls over back to 0. And then you can increment a global variable to count the number of times it's rolled over. And that global variable can be as big as, easily can be just a 32-bit if you want, which would essentially add 32 or like 16 if you want. You can add 16 bits to the left side of the counter, essentially, by doing it that way. So how do we do that? Well, first we have to set up an interrupt for that. So how do we go about doing that? Well, the first thing you want to do is enable interrupts for the rollover functionality. Now the counters they're kind of complex. They have 3 different control registers, A, B, and C. I think I only have one of them shown here, though, for simplicity. It's the B one, so TCCR1B. This one is where you control the prescaling, which is what I was talking about, and so you can also have it trigger on an external clock source. So these would be 0. These 2 bits here, 7, 6 would be 0. And then you can have no clock source, which would stop it, or you can set up the prescaler. So generally, in this control register, I just set up the prescaler. And then actually, where is the, okay, I don't have it here for some reason, but that's no problem. So if you bring up the data sheet, which we have available on the website. I just have a bookmark to it. I refer to this quite a bit. So you'll find that the lecture slides and sometimes even the handouts we give you don't have all the information you need. If you're looking for something that might not be there, just go to the data sheet. So the timer control register is TCCR1B. So I can look at TCCRN. So the 1 here, by the way, too, is referring to counter 1. So this is the only 16-bit counter. The other 2 are 8-bit. But aside from that, they behave the same. So if I look for TCCRNA in the data sheet, TCCRNA, I can just do a search. I'll eventually find the bits of that. Oh, no, maybe not. Okay, how about just TCCR? Ah, yes, okay, so I'll just put 1 instead of N. Yeah, that's right, they have them defined separately. Okay, so there's register B, and this one's got, you can actually control, you can do things like control this PWM functionality, pulse width modulation. You can also actually have it overflow at a value other than it rolling back to 0. So you can set a top value as well, which I've used, but you can also just, if you want it to interrupt after a certain amount of time elapsed, you can also just set the counter, you can initialize it at a certain value such that when it does overflow back to 0, it'll be the amount of time you want. You guys with me? Right? Which I talked about a little bit last lecture. Okay, so this one's got, let's see, there's bits here, but this is not the one I'm looking for. I'm looking for the interrupt bit. So that would be in A.
If this seems a little bit intimidating surfing around data sheets, it kind of can be at first, but after a while you learn which registers matter for the functionality you want, and it becomes kind of a quick figuring out what prefix you need to search for, and then just jumping to that part of the data sheet to check and make sure you're setting the bits right. Usually in the handouts, we kind of shorten the process, and you get to see a sort of like highlights view of the important registers to set. But if you have to figure this stuff out on your own, you wind up data sheet surfing kind of
Yeah,
like this.
which is what I'm doing.
Yeah. So Dr. Bekos mentioned pulse width modulation. That stuff is really cool, and it may come up in a future lab. That allows you to, if you have an LED hooked up and you change the PWM timer values and stuff, you can actually fade LEDs on and off. Real life example would be, I once actually built light up greeting cards this way for a local design firm, and had to use the PWM registers specifically to get all that stuff to fade on and off the way it was supposed to.
Do those registers like control the symmetry? Like, can you specifically say like add like a 40% duty cycle so you can control the
Yes.
Yeah.
voltage?
You do have the ability to control that, and I think it even lets you set whether you want to have a sine wave or a sawtooth wave,
Okay.
and possibly even, it may support square waves. I'd have to go back and check.
Does it just depend on the chip, like the kind of options you get with it?
In the case of, like in the general case for all embedded systems, it'll vary. For the AT Mega, check the data sheet.
So this is what I was, thank you, Philip, for buying me some time. I appreciate that. So this is what I was looking for. I'm sorry, it wasn't in one, the reason I was confused is it's not in one of the 3 control registers specific to that timer. It's in the interrupt mask register, actually. That's the TM mask 1, and the bit in there that I was looking for was this one, which is the, output compare match, this one, sorry, TOIE1, which is the overflow interrupt enable, right? Which I do think I think I had that in the slides. Let me double check that. Let's keep clicking the wrong. There we go. So we've got TCCR1B, which is controlling the prescaler, and then yes, here we go. Yeah, I did have in the slides. It's this one here, TM mask 1. I knew I had all the information we needed here, and the bit is TOIE0. You guys with me? Okay, so so what does that mean? It means we've got 2 registers we got to set. We got to set the prescaler value, and we have to set the interrupt enable if we want it to interrupt on an overflow, and then we have to define our interrupt handler for that. Okay, so if we go back to the code, let's see. Let's go up to here. So we'll just put this stuff. We'll do our initialization right here above the while loop. So, so the first thing we'll do is we'll initially disable interrupts with a CLI, right? Which is I think they're disabled by default even if we didn't do the CLI, right?
Yeah, I think as part of like the prologue that GCC is going to stick in there, it usually disables the interrupts while it's setting up all the vectors and stuff. So.
And as a matter of fact, I believe all of the individual interrupts are disabled in their respective mask registers as well. So even if the interrupts, even if I had enabled the interrupts here, none of them would be triggering anyway. But the CLI is a global interrupt disable. It disables everything. And the reason I'm doing that is because I'm going to enable the counter one, and I don't want it to trigger until I'm ready for it to trigger. So there's TM, and I always have to flip back and forth. It's the T. Well, we can set well, let's set this one first. TCCR1B. So TCCR1B. And we will set the, we want to set the prescaler. Now in this case, because the prescaler bits are all consecutively placed in this control register, we can just put a binary value from 0 to 7, or 000 to 1111. So in this case, if we want to do, like, say, 1024 prescaling, we can put a 5 in here, because the 5 will map directly into these three bits. And we should also shift it by CS10, although it's, that's 0, so it's not going to make any difference. But we'll do that anyway. So the shift amount is CS10, CS10, and then instead of shifting a 1, I'll just put a 5 there, right? So that's going to set the prescaler to 1024. And then for the interrupt enable, that one is in the TI mask, I think. TI mask 1, and the bit there is TOIE1, TOIE1. So TI mask 1 and TI mask 1, TOIE1, right? TOIE1, right? All right. So that'll enable the overflow interrupt. Okay. So now the other thing is you can initialize the count itself. So TCNT1 is the count. Now this is a 16-bit value, and setting the 16. You'll notice in the data, or you might notice in the data sheet if you look this up. Setting a 16-bit value is a little tricky. You have to write the most significant 8 bits first, and then the least significant 8 bits. But you don't have to worry about this in C, because the compiler generates this sequence of instructions correctly. So you can just set this as if it was a 16-bit value. I'm just going to reset it to 0 for now. Okay. So now that we've got the interrupt set up, we can also enable the interrupts at this point, which is SEI. And then if we want to write an interrupt handler, we can just go anywhere outside of main. I can just put it right here. And we just have ISR. And then we have to figure out what the interrupt handler for this is called. And I can never remember that either. So I'm going to look in, it's lib avr. Or lib, user lib avr, include, then it's avr again, redundantly, and then iom, iomega, yes, 328p .h, right? No? Oh, iom 328p.h, right? There we go. Okay, and then in here you can just search for _vect, and it's usually not too hard to find. So there's our interrupt 0. So we've got timer 1 overflow. There it is. So that was pretty easy to find. You can take that and copy that, and then let's see, we can paste that in there. And there we go. We got an interrupt handler set up. So every time that timer rolls over, it's going to call this function. Okay, so what do we want to do in here? We want to increment a global variable. So volatile uint, let's see, 16. We'll call it overflows. So we'll have this overflow counter, which will be global. Unfortunately, this is the only way I know how to change state inside one of these interrupt handlers, because you don't get like a void pointer to a struct or something. So the most convenient way to change things in a handler is to have a global variable. There might be a better way to do it, but this has worked for me. So once we enter this interrupt handler, we can just increment overflows by 1. And so this way, if we take the overflow variable and then we concatenate it with the actual count, we get effectively a 32-bit counter. Yes?
What's the reason for the volatile keyword?
The volatile. So the volatile is normally what it means is you want the compiler to treat it as though something else might be changing it, right? Aside from the actual program code.
And since this is always going to be getting hit with the interrupt, you want that to be ready.
Well, this is the only code that's going to be changing it. So I think I'm not even sure how needed it is, right? It's kind of a convention we followed,
I
right?
just kind of do it for safety purposes, because like normally volatile is if you have if you're aliasing a variable on top of an I/O register or something that's going to be changed out from under you by the hardware, you want the compiler to not make any crazy assumptions about that variable like holding a value, because it could change at any moment. So
Yeah. I think in this case, like,
for all our globals, just as a matter of course.
yeah, because like if you're in the while loop in main,
Yeah.
and the interrupt triggers, goes to the handler, increments that, and comes back, right? The code in main doesn't necessarily know that variable's been updated. So if it were allocated in a register, right, you'd want to make sure that you reload from that register. You don't want to make assumptions about the value of overflows being in a register. In other words, you want it to generate a load instruction every time you reference the variable, just in case it was changed outside that basic block or that block of code, right?
Yeah, just one last thing to add to that is like if it didn't do the fetching every single time that variable's referenced in your code, and we just had uint16 overflows equals 0 up there, the compiler might not know that we expect this variable to change out from under us periodically, and it might make optimizations in our while loop there, thinking that it's going to stay 0 the whole time. So, like for example, if statements might not trigger when they're supposed to, and other stuff could break. Whereas if we stick volatile on there, the compiler's like, oh, this is dangerous. This could change at any time. I need to load it fresh every time I see it.
Okay.
Which is, for stuff that you expect to be hitting with an interrupt handler, that's like a really good thing to have happen.
So to point out, if you're using pointers, it will always do that unless you mark it restrict.
Oh, yeah. Yeah, restrict is a really wonderful keyword that is a weird feature of this C99 standard, I think was when it came out. And it allows the compiler to make optimizations, but if you've never heard of it, don't worry, you're not missing out on much. It only matters for heavy numeric code. All right.
Okay, so what do we want to do with this? Well, how about let's see, we can randomly choose, we can choose a random number, and then we can use that to control the rate at which the LED toggles. Make sense? The problem, though, is that if I just use overflows, it's going to be in increments of 4.1 seconds, right? So maybe on second thought, using the 1024 prescaler might not have been the best idea. Let's look at some other options here, because I can change that easily. So 65,536 times, there's a 64 prescaler, right? And I divide that by 16 million, that gives me 262 milliseconds. Or if we don't do a prescaler at all, it's 65,536 divided by 16 million. That's going to be 4 milliseconds. So if I were to multiply that by a random number, that's a 15-bit number. Let's see, times 32,000 gives us, that's like 2 minutes. Yeah, that'll work. Okay, so let me do that. Let me, actually, I'm going to turn the prescaler off in this case. So I'm going to just go back up here and set this guy to 1. And then I can have a variable uint. Let's see, uint 16 underscore t weights equals random. This should give me a number between 0 and rand max, which I believe is 0 and 32,767. And then I can say, I can have a counter. So uint 16, say count equals 0. And I could say, while overflows Doing something wrong?
No.
Okay. While overflows is less than waits, then do nothing. Now hopefully this should work. Right now this misspelled overflows. So this is going to keep watching the overflow, and it's going to it's going to randomly grab a value between 0 and 32,767, and it'll wait until the overflow value gets that high. Once it does, we can reset overflows. And overflows equals 0, and then we can toggle the light. So so we can say port C equals not port C. And then we can get rid of all this stuff down here. All right. Make sense? Did I turn off, let's see, overflows? Okay, so yeah, I don't turn off interrupts everywhere, so we should be good, right? Okay, so this is going to be anywhere between, now the only problem though is that what happens if I get 0? Well, that's unlikely to happen. So this will be anywhere from, let's see, well, 0 would be no wait. 1 would be 65,536 divided by 16 million. So 4 milliseconds, and then if I get the large number, divide that by 16. That could be as high as 2 minutes. Okay, so that could be, let's just see what happens. Hello. Okay. Okay, TCC1B, that was a typo. There should be an R in there. That's line 97. All right, no problem. Okay. Okay, it's off. Guess we're still waiting. Maybe we should divide the random number, or we can mod it. Yeah, yeah, that's a good idea. I haven't tried mod yet, though. I assume that'll work on this chip, right? Should be okay.
Behind the scenes, it might be inefficient, but it'll work.
So what do we want to mod it by? Let's say 1024 maybe. Actually, I just do a and with 1 shifted by 10 bits and then -1 to do a mod by 1024. All right, make burn. There we go. So it came on. And it goes off. There you go. Still a little slow. It is working though. There it goes. Let's speed things up just a little bit more. Let's mod it by 256. There we go. There you go. There it goes. Any questions? Yes.
So, just maybe a little bit. You said that for 16-bit assignments, it's actually 2 instructions.
Yes.
So, does that mean that like this overflow assignment is non-atomic? and if you have an interrupt in between, you could have a like where half of the field has been set. But
Yeah.
half message, okay.
Yeah, I probably should have disabled interrupts there. That would have been a safer. That's a good point. Yeah, that's a very good point. So I can increment overflows here and then disable them in the handler. So I could disable them there, and then not re-enable them until we're ready again. So let's see, where do I reset the count? Oh, I don't reset the count. Probably should be doing that too. Okay, so let's see. So basically, once we, the only problem with that though is that, we can't, we don't want to disable it here because there's nowhere to enable it down there. Again, because we're in a busy loop. Sorry, what was you going to say?
I was just going to say, I think you can just disable it around the assignment.
Of overflows, yeah, that's a good point.
So I suppose then you have the problem that you could miss an overflow, but I guess that's probably better than...
Yeah. Yeah, so that'll kind of make it atomic. That's a good point. Yeah, you could disable them and then reset overflows and then re-enable them there. Right. Okay, any questions about this? Okay, so what else can we do that's kind of interesting? So how about we create a thing where after a random amount of time, it'll turn the light on, and then when the user sees the light on, they have to hit a button, and then we'll use the timer to record the reaction time, how fast the user was able to react to the light coming on, right? So we have the counter is incrementing at once per cycle. We've got overflows, so between the two of them we can record time. So let's see, how would we change the code? So after this while loop, we'll turn on, we'll just turn on the light. Right? And then we need a way to be able to determine when the user hits a button. Now you could wire a button up externally, which I've done it that way before, where I just put a button on the breadboard and wired that up to one of the interrupts. But I didn't bring a breadboard with me. So an easier way to do it is to use the UART console, right? So it turns out that the UART actually has an interrupt. So right now we've got it set up, we've got the boilerplate code in there that allows you to use printf and also scanf to read and write data from the console. And it does it sort of in a polling approach, right? If you do a print, it'll sit there and print each character out until each one gets printed out. So it'll wait, it'll actually spin. In fact, if you look at the boilerplate code, you can see where it does that. It's up in the UART put character. So there's a call that says loop until bit is set. So this is going to spin until it's ready to send each character out, right? Likewise, the get char, that's put char, get char does something similar where it does a loop until bit is set, it looks for this bit. So another way to do this is to have an interrupt that's triggered whenever the UART receives a byte, right? So there's, if we go back to the slides, I always hit the wrong button. And find UART. So I've got a section here for that. Okay, so there's a control register, and let's see, where is it at here? There's obviously there's multiple. So there's A, there's B, and there's an interrupt enabled. So you can see why I was confused, because with the timer has 3 control registers, A, B, and C, but you don't set the interrupt in there. There's that mask. But for the USART, you actually do set the interrupt in one of the control registers, which is kind of confusing because it's kind of hard to find where all the interrupt enables are. But in any case, this is UCSRNB. So the N, by the way, is a number, that would enumerate which USART controller, but we only have one. So I believe the only one we've got is UCSR1B. So if you set that, we can set it right here where we set the timer, which is this guy. Let me just set my tab stops. So it's UCSR1B, 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 and we set the bit called receive complete interrupt enable, which is RxCIE1. RxCIR1. R1? Or is it 1? E, sorry. Sorry. EN, it's EN. Or, hold on. Yeah, you're right. RxCIEN, yeah. All right. Okay. All right, so that'll set up the interrupt, and then of course we need to find the vector for that. So first, let me up here. So ISR, and then we look for what is it? 60, 79. Okay, we're looking for USART. So there it is, USART. That's pretty nice. USART RX vect. So we come back up here and do USART RX vect. All right. Okay. So what do we want to do here? Well, when they hit a key, first thing we should do is disable interrupts when we start this guy. Oops, CLI. When the user hits a key, we want to record the count, the timer. And we can actually print that. Oh, also, the other thing I found is that if this interrupt triggers, it'll trigger again immediately after unless you read the character out of the buffer, right? So how do you do that? If you look at the boilerplate code for getchar, it's really just 2 lines of code, but this is the critical line here, this return UDR0. When you return UDR0, that registers, that will create a load instruction, or actually probably an IO instruction, for the UDR, the data, that's the byte that comes in. And you have to read that, even if you don't do anything with it, you have to read it in order for the interrupt to drop, in order for it to stop interrupting for that character, right? So I think the easiest way to, I'm going to be kind of quick and dirty here, but we have to read it even though we don't want to do anything with it. So luckily, the compiler is not very aggressive about optimizing out dead code. So we can have a volatile uint8 type called foo, and then whenever this interrupt triggers, I can say foo equals UDR0. So that'll be enough to read to convince the chip that we've read from the buffer. At that point, we can actually print, let's see, printf. Actually, I'm just going to set a flag. Pressed equals 0, pressed equals 1 rather. And I'll have a volatile uint8 pressed equals 0. So that'll be a flag that'll get set. And then it will return, actually I should enable interrupts again, I guess, after that. Actually, no, not yet, I'll do it in main. Okay, so the first thing we want to do is we want to wait for a random amount of time, which we've already got in here. So we get a random number of waits. This will pause. Once that returns, we'll do a CLI, which will disable interrupts. And then Actually, I want to set port C to 1, so that'll light up the light. And then I am going to say pressed equals 0, and then overflows equals 0. So I'm going to reset both the flag that says they haven't pressed the button, and I'm going to reset the counter. I'm also going to reset T count as well, T count 1 while I'm at it. And then we'll re-enable the interrupts, and then we can have another while loop that says while pressed equals 0. And so that'll wait until they press, and then at that point we can print a message. Actually, we could turn the light off. So port C equals 0. And then we can say your response time is, and then I'm going to print an unsigned long, or just long? This is going to be a 32-bit, so long, I think, right?
It shouldn't cause too bad a mess up if it's the wrong type.
So that's going to be overflows shifted by 16 and then ORed with. By the way, one of the things that always very commonly screws me up. One of the, C's order of operator precedence is usually pretty obvious, but you have to be careful with shifts, because shift operations have a very low precedence. So it's very often, it can happen where if you don't put parentheses whenever you do a shift, you can end up getting a bug in your code, because it'll end up, like if you have another operation here, which is what I'm about to add, I want to OR this with T count, right? So T count is a 16-bit value. I want to concatenate that with the overflows shifted left 16 bits. If I hadn't had parentheses here, I think it would actually do the OR before it does the shift. So you have to be careful with that, right? And since we do a lot of shifts in this class, you need to make sure you remember that. Okay, and then we already turned the light off, and then I guess we just repeat, right? We need to get interrupts back on, which I already did down here, but I should probably, actually I'm going to do that up right. I'm going to turn them on here. Oh, SEI. All right, I'll turn interrupts on right before we wait. Should probably reset count there too. Maybe I'll reset count. T count, so reset the counter, enable interrupts, then we wait for the overflows to reach the value we want, and then I will disable interrupts, turn the light on, reset the pressed overflows in T count 1. Oh, sorry, that should be T count 1 there. So in other words, we're using the, sorry?
Down in the print as well.
Oh yeah, sorry, thank you. So what is the point of this? Well, the point is, notice that we're using the counter for two things here. We're using it to have a random delay, and we're using it as a cycle counter to give us a very fine-grained way to time things in terms of 16 millionths of a second, right? Okay, so hopefully that will do it. I already have my terminal open here, so I just have to be in that terminal and be able to hit the button when I see the light, assuming this works. So we can do a make burn here. Let's see, I have an error. Yes, that would be line 27.
83.
Oh, sorry, 83, thank you. Unknown type, oh, that's a typo. uint, this should have been a 8, right? And then we had another one here at 108, which was, oh, sorry. Oh, that wasn't right, RxCI enable? Okay, so that's no problem. I'm just going to go back to the, sorry?
Shouldn't it just be 1 instead of n? Like the
Oh, yes, you're right. Thank you. Yeah. I always get fooled. Yeah, because in the data sheet they use n. I always get screwed up by that. All right, make burn.
Oh, you may need to cast overflows up in order to shift it.
Oh, right. Yeah. Good point. To a 32-bit value. Yeah. So let's do that, because otherwise it might shifting it by 16. Since it's a 16, it'll just shift everything out. So uint 32 type. Okay, and then let's see, line 108 again. Sorry about this. RxCIE1. Okay, that's fine. I'm going to check the it was 82. RxCI. Oh, E0. Oh, that's it. Oh, okay, right on. Okay, sorry. RxCI E0. It starts as 0, not 1. Sorry. All right, that hopefully will do it.
Oh, is that true for the UCSR as well?
Yeah. Line 1, same place, 108. Sorry. 108. UCSR 0B. 0B. Yeah, so the 0 refers to the first UART, but we only have one UART. Okay. All right. Now, didn't work. Well, let me reconnect just in case. Yeah. Okay, didn't work. All right, so what did I screw up here? I had this working earlier today, so I know it's possible to do this. I might have just screwed up when I had the interrupts enabled and disabled. I bet I didn't re-enable. Yeah, that's what it was. Because I disabled them here. Yes, and I don't re-enable them before this while. So that was the problem. So I need an SCI here. That way I can so I want to enable the interrupts for my overflow thing, and I want to enable them for my key pressing thing. So I have an SCI, and then actually I can disable, might as well disable them after I get done with this while loop. Right, so, all right. And there, okay. Still not working. While pressed equals 0. So I set pressed equals 1 inside there. I read it here. I also disable the interrupts inside there. The interrupt enable is here, UCSR0B, UCSR0B, or with one RxCIE0. Let me put a print in there. See if this is triggering at all. Rx interrupt. All right. No, it's not triggering the interrupt. Okay, I'm going to cheat a little bit and look at my other code that I wrote earlier to test this. Okay, USART. So first of all, the interrupt service routine is USART RX vec. Did I get that right? USART RX vec. Okay, that's correct. Yep. Press button equals 1. I read the UDR 0 the same way. Okay, and then put share, blah, 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 blah. Okay, init, main. I set UCSR0B, UCSR, and it's RxCIE0, so I do that the same way. All right, so what am I doing differently here? It's got to be me having these things disabled. They're enabled before the overflow wait, and then they are, I know it's getting past this because the light comes on, and then, oh, pressed is volatile, right? Yep. And it does get set to 1 inside the interrupt handler, right? And so once that's 1, 1 doesn't equal 0, so it should come out of there, disable that, and print the message. The problem is, yeah, but the problem is it's never getting set to 1 because it's not calling the interrupt handler. I don't know what's going on with that. I can try, let me load this one. Maybe it's a connection problem here. So make burn. Okay. Yeah, so this one's working. I don't know what the heck's the difference that they're yeah, so basically in my original code I used to test this, it actually says, you know, wait for it, and then there's a random delay, and then it says go. Of course, it's really fast now because I cranked it down to be, the random wait is really slow when I was testing this, but yeah, it prints out. I don't know if you guys spot anything that looks different here.
There was something, so where's the RxC0 you're setting in the RX spec?
RxC0 or RxC, what is it? So yeah, that is the, that is a flag that indicates whether you've received a byte in the USART. If you're using interrupts, you don't need it. When I originally wrote the code, I cleared that bit because I thought that was why it kept triggering the interrupt. But it turned out that wasn't it. You actually have to read the UDR0 in order for it to stop triggering the interrupt. So that, when I put that in there, it didn't make any difference. Clearing the flag didn't do any good. In fact, I think that flag gets cleared when you read UDR0. It gets cleared by the hardware, so you don't have to do it as a program in your code. But yeah, I know what you're talking about. Inside the handler, which I don't do it in the one on the top here, but in the one on the bottom, I'm doing that down here. So yeah, the vector looks the same. USART RX vect. I disable interrupts as one of the first things I do, just as before. Set it up the same way. Let me just double check that. Which is done right here, UCSR0B. That gets set. I wonder if there's something else in that control. Maybe I should nuke everything else in that register. Of course, I didn't do that before. I shouldn't have to do that.
Yeah, this is your working code.
Yeah. Oh, sorry. Yeah, you're right. Sorry, I'm in the wrong code. Thank you. Yeah, so I didn't nuke everything in there before. USCR0B. You know one thing? Oh, I know what it is. In the code below, I called init UART. That was the boilerplate code that set up the. So I never initialized the whole UART subsystem. You know, setting up 8 bits and all that kind of stuff. 8 data bits, 1 stop bit, the baud rate. That's what I'm missing. Sorry. So there's a function UART init. So I'll call that, and that should fix it. There we go. All right, so downloads. Yep, there it is. Okay, that fixed it. All right, so lights on, hit a button. Oh, the random, oh, it's going really fast. Come on. There it is. Hold on, I got to make the time. This is not any fun. Hold on. I need to take that shift out of there. Or not the shift, but the modulo. Let's bring this back up to, say, 10.
Also,
Here.
just type in LL cycles.
Yeah, actually storing it. You gotta do LLU instead of.
Oh, yes, thank you. LLU, yes, sorry, thank you. Yes, thank you. Had the wrong order there. Okay, cool. All right, make burn. Oh, I just hung it. Okay, I think it should have just been L. Sorry, not LL. LL must be 64 bits, I imagine. Yeah, you know what? I looked this up, and I was surprised that. Okay, it's off. Okay, yeah. And okay, so my response time is about 3.6 million cycles, which you can convert that to seconds. Obviously, divide by the clock rate. But in order to do floating point prints, you have to add a -L printf in the make file. You have to do -L print underscore FLT. -L printf FLT. You have to include a library to enable floating point printfs. Otherwise, if you try to print a float without that, it'll just be blank. It doesn't work. And if you do put that on, it may use up all your memory. I haven't tried it yet, but it's going to use more code space. That's the reason why I just printed the cycles, and then you have to do the arithmetic yourself to figure out what that translates into in seconds. But obviously, it's this divided by 16 million. Yes?